Welcome back. So we're going to start into chapter 4, 4.1. I did get all the exams scored, as hopefully you've seen in the grades. Some of you did better, some not, but it's we ready to go? All right. So kind of think of what you did the first one, what you did this one, what was the differences. If you improved, keep doing that. If you did a little bit worse, maybe look back and remember the lowest score gets dropped or replaced by the grade on the final. So it's kind of keep going and hopefully keep improving. And that final can help out. Yes, sir.
I just have a quick question. What if, my final is lower than my lowest grade?
Then your other ones will stick. The final will be what it is. It goes in the final, but your other ones, only the lowest one. So we're not going to lower your grade. Yes, hopefully the final is better. Also, you can continue working on the homeworks from the last section until Sunday night. I have them open until then. I did do an update on grades, so those are there, but they're not final. If you get something finished, it'll get updated next week because you have till Sunday night. So I'll do probably again Monday or Tuesday. I'll re-update to get the final scores in there. Okay, in about 2 weeks, a little less than 2 weeks, we have our mastery test. I will over the weekend. I'll post the review for that. It is 20 questions, and it is just find the derivative of this. So it's all sorts of different types of derivatives. The questions are all multiple choice, so you just have to recognize the derivative. So even if you may be having a few problems, you might be able to just from the list pick it out. Okay, but we'll get ready for that. We do have one whole day to review for it, and really you have enough information, enough knowledge of what we've covered so far. That's going to be on the mastery test. What we're going to do in the next few days, today and then next week, in chapter 4, we're still working with derivatives, so it will be a good opportunity to practice. It's good, at least the parts of taking derivatives. Okay, because what we're going to do now is we're going to apply the derivative to solving some problems. We're going to see what the derivative can give us. All right, so 5B is now open. I did realize that I didn't have the thing clicked, so you wouldn't have seen it before probably about noon whenever I turned it on. So our first module here, maximum and minimums, the slide deck is in there. After we finish here, I'll upload this evening, I'll upload the video, so that'll be there too. So before we start into it, any questions? On the mastery is just derivatives. Yeah. So it's just seeing if you can master how to take a derivative. Now it may have chain rule, product rule, but it's just, here's a function, give me the derivative. That's all it is. No word problems, no linear whatevers or, approximations. And you can do it, because all you have to do is choose the right answer. So you could do it any way you want. You can do it with technology, whatever you want to do. So we'll work towards that again. I'll put the resources I have from the coordinators already there, and then I'll see if I can maybe make a few maybe a few brief videos of what to focus on and that kind of thing. But it's 20 it's 20. I'll look at the detail. Basically, it counts half of one of the tests, so it's not as heavily weighted. You don't have to get 100% on it. You don't even have to get 50% on it. But it's, of course, the better you do, the more it will help out your score. So at least when I was at the community college, they had you had to get 80% on their mastery test or you failed the course. Even if you got good on the exams, you had to get 80% on the mastery test, which I disagreed with, and that's why I didn't teach calculus there. So, okay. So today, let's go ahead and get moving. We're looking at maximum and minimums. And we could do this without calculus. We don't have, I mean, we could just look at the graph and we're going to, you know, what you think a maximum looks like, that it's the top of a mountain, that's what it is. What you think a minimum looks like, the bottom of a valley, that's what it is. Okay, so it's going to be pretty straightforward. We can use algebra for most of these. We can do it by graphing, which we will do to look at things, but what we're going to do is see that we can also apply some calculus, and that's just taking the derivative, and basically we're going to see it's where the derivative equals 0, because that's a horizontal tangent line, right? Slope of 0 is horizontal, so that gives us either a maximum or a minimum. So that's basic, that's the whole story of what we're doing today. Here's our schedule as we go forward, so you'll see next week we'll do a little bit more in chapter 4. None of those things that we're doing now will be on the mastery test. Again, the mastery test is just about taking derivatives, but by working through these next things, because you will be taking derivatives, it will reinforce your derivative taking skills. Okay, we'll do the mastery test, and then we'll continue. We'll finish up 4, we'll do 5, we'll have another exam, and then we've got 2 more sections, and then we've got a final exam. So as far as content-wise, not too much more to do. Okay. So there's 2 kinds of maximum minimums. So a maximum is the highest y value. When we're talking maximum, we're talking what has the biggest y value. There's an absolute maximum or minimum, highest of the high and the lowest of the low. There's also what we call a local maximum minimum, which means in its area it's the highest or the lowest. If you're driving down the road, a pothole is a local minimum. The speed bump is a local maximum. Okay, it's not the highest place in the whole city, but for that part of the road, it's the highest point. Okay, so just think of that. We're going to have 2 kinds of maximums or minimums. The definition for an absolute maximum is, you know, it's kind of wordy, but it's basically saying that the y value of the function is the biggest y value of any other value, of any other x value. So there's 2 things to kind of keep straight. We talk about where they occur or location of a maximum or minimum. That's an x value. Okay, the location of where it happens is x. The actual value is the y value, the output value of the function. Okay, and sometimes it's easy to get those mixed up. But it's just saying we have an absolute maximum whenever the y value is bigger than any other one in the function, at least on that interval, on that domain. And we have a minimum if the y value is the smallest y value. Could be negative, could still be positive, but it's the smallest one of any other y value. Or at least there's nothing smaller. There could be something equal. So you could have 2 areas where you have 2 places where the absolute minimum occurs, but the value of the absolute minimum would be equal. There's only one value. Could be more than one location. And the local is just sort of defining it. It's when we're near a particular point, sort of in a neighborhood, that we have either the largest or the smallest. There could be others out there. You know, Mount Everest is a lot higher than Camelback Mountain, but if you're in Scottsdale, Camelback Mountain is probably like a local maximum. And if you're in downtown or back South Phoenix, probably it's South Mountain that is your local maximum. Yes?
So basically the local maximum or the minimum could be even given range.
Yes, yes.
There is no range for the absolute.
Right, absolute is like we consider the whole function, and it could be if the function, if we consider the whole thing, it could be infinity, because it could be, so sometimes we say it's infinity, sometimes we say that there's not really a maximum because infinity is not really a number. So we just look at the context of what they're talking about. Okay, so now what do these look like? So we'll do it graphically. Well, here's an example. We have a local minimum here because we're down, and in this area it's the smallest y value, but we see over farther to the right there's a lower y value. Okay, so for this, at least what we're looking at, we could call both of these minimums local minimums, but this one at K is actually an absolute minimum, at least for the picture that we've got. Okay, and then we've got a local maximum here, and it's not an absolute maximum because we see that it's over here, it's going to go up higher. Okay, just looking at that picture, where would you say that maximums and minimums occur? Visually. What's that? Where the slope is 0, because it's like either the top of a mountain or the bottom of a valley. And so, yeah, the tangent line there would be 0. There's 2 other places that sometimes we forget about. Where else could a maximum or minimum occur without this? Oh, we could have an asymptote, so it's going to infinity, but there's also another. If we have a limited domain, let me preface it. So if this was the complete graph, or the domain we're looking on, where else could there be a minimum or a maximum? Endpoints. And those were the ones I always would forget about. You check your endpoints, okay? So we're going to go through a process when we ask for minimum and maximums, and part of the process is check those endpoints, because they could be it. Don't just look for where the derivative 0, we do that, but also look at the endpoints. Are there always maximum and minimum values? Constant function, then every point would be a minimum or a maximum, right? So that could happen. We talked about one, what if it shoots off to infinity? Either way. That's not really a maximum or minimum, because it doesn't stop, right? It keeps, whatever you say this is the maximum, if it's going to infinity, it's going to be higher. So that would be the one place. But if we have a boundary, if we limit the domain, then we are guaranteed that someplace, maybe the endpoints, there will be extreme values. There will be minimum and maximum. It could be that everything's a minimum or maximum. So that's one possibility. But if we have it going on an interval from A to B, so we've limited, we've got an endpoint, it's got to stop somewhere. And it could be high and it could be low. So we'll get generally both a minimum and a maximum, but that's what it tells us. So the extreme value theorem, and there's this whole proof, it just supports our sort of thought. If you're going to limit it here, somewhere between here, there's going to be a high point and there's going to be a low point. There could be multiple ones, everything, so we could look at that, but there is guaranteed to be minimums and maximums. And here's a few examples. So we have this one that between A and B, there is a maximum at C and a minimum at D, and those are absolute minimums and maximums. You could also call them local, because they are, for that area, they're the highest or the lowest. Here in the middle one, C is a maximum, and then at the minimum is actually going to occur at an endpoint, at B, right? And when we talk about minimums and maximums, again, we're talking about the Y value, but we identify where it's at by its X value. That's the keyest part that is easy to get confused. Oftentimes I'll ask, where is it? That's the X value. What is it? That's a Y value, okay? And I know in our college algebra, they do the same type of thing. They don't use calculus, but they ask those two things, but the way they ask them, it's very easy to flip them, to put the X where the Y goes, and then it gets marked wrong. The last one, again, we've got a minimum at D, and it is at absolute minimum. And then we have two places where the absolute maximum occurs. Notice the absolute maximum is the same value, whatever this is, but it occurs at 2 places. So there's still only one maximum value, but it does occur at 2 places. There would be 2 X values we could list it at. And the endpoints are neither maximums or minimums. So that's what it looks. How do we find it? Well, we kind of talked about it. Since the tangent line is going to be 0 there, we could take the derivative, set it equal to 0. And that's what Fermat's theorem says. Fermat also had Fermat's last theorem. He wrote something in a column that he never proved, but I think someone actually finally proved it after like hundreds of years. I wish I was that guy, but I remember when I was starting off in my undergraduate work, it hadn't been proved yet, and that was a big thing of who's going to be the person that proves it. In fact, the thing is just because he said it was true doesn't mean it really was. He just said, I have a proof for this, and then he died. But then somebody found a way to prove it. But that's another one of Fermat. This is not his last theorem, but he found a theorem that basically, if the derivative is 0, you're guaranteed that you'll have a minimum or maximum. However, we could also have a minimum or maximum at a place where the derivative does not occur. So we might have a V, a sharp point. We can't take the derivative there, but that would give us a minimum or a maximum. So it's possible still to have one where a derivative doesn't occur, but if the derivative does occur, it has to be a derivative of 0 in order for it to be a minimum or a maximum. If it's not, that means we're still going up if it's positive. If it's negative, we're still going down, so it's not a minimum, right? The only time we get one of those is if the derivative is equal to 0. So we're going to talk about something we call critical numbers. Now, I noticed in this book they haven't started talking about critical points, and that's where I got confused a lot of times. Critical numbers are the x values. Well, what are they? They're the x values where the derivative is 0 or the derivative does not exist. So they're candidates for either minimums or maximums. They don't necessarily guarantee it, but they're pretty good places to look. So part of the activity will ask you find the critical numbers. Those are x values where the derivative is 0 or the derivative doesn't exist. Okay. And then we evaluate them to see whether we've got a minimum or a maximum. So those are the theory part behind this. Way we go about finding minimums or maximums, if we're looking on a closed interval, we'll probably look at some on an open interval, but today we primarily focus on the closed interval, which means we have a start and a stop. We go to look for all the critical numbers. So that's, we take the derivative, set it equal to 0, find where those are, and then try to see if there's any place where the derivative does not exist. So maybe if we have like x minus 4 in the denominator, it wouldn't exist at 4. So we look for those. Notice number 2, we don't forget about those endpoints. That's the next thing we do, is we get the values at the endpoints, because those might be our minimum or maximum. And then we take we've got everything we need. So we find the values of the critical numbers, and then we actually get the critical point. So we've got the critical numbers are the x value. We plug it in and get the y value, and that's called a critical point. So then we compare all the y values. The biggest of the big is the absolute maximum. The smallest of the smalls is the absolute minimum. Okay. All the others will probably be local. And then again, the example we'll look at, we'll do it both ways. We'll also do it graphically, and you'll see how it all works out. And actually, I do it backwards. I do the graphical first, because then you see it and you know. And when you know where you're going and what you're doing, it's so much easier to get there. When you put a blindfold on and try to get someplace the first time, you trip over all the furniture or something, So we'll do that. So let's take a look at this example. We're going to do it both ways, graphically, and then we'll follow that 3-step. We'll do the critical points, critical numbers, which give us the critical points. We'll look at the endpoints, and you'll see once we look at the graph, it almost becomes easy. Well, it does become easy. But we got to look at the graph first. And so I need Desmos. Let's see, how do I get there? I think I go there. Two x cubed. And again, while we can't use Desmos on an exam, I do recommend using it as you explore, because it's easier to work with and it shows it up better. And then work with your handheld to be able to sort of replicate some of these. But as far as the learning, Desmos provides some really nice features. So what was it? It was 2x cubed minus 3x squared minus 12x minus 3x squared minus 12x plus 1, and from negative 2 to 3. Plus 1? Or was it minus 1? Okay, see, I forget so easily. And then what I'm going to do is I'm going to put the curly brace and go from negative 2 less than or equal to x less than less than or equal to 3. Because I just wanted to show the domain. Okay, and I'm gonna kind of zoom out a little bit. So that's a way we can actually, so this helps us focus on the endpoints, right? Because if we graph the whole thing, it's going on forever, and this does it. I'm also, just to make it look a little bit better, let me zoom in on the x's. Let's see, let's go -10 to +10, so we can kind of center in on this. I think our y's are okay, but let's go -25 to 10, and we'll be able to see everything we need to see. Okay. So graphically, we could just look, and can you see where a maximum might be? Not even hiding, is it? It's just right. Yeah, there it is. And we could click on it there. And what's that point? That's a critical point. The derivative at that point is going to be 0. When x is -1, we'll see that. And we'll do it also by hand. And then we see the minimum. And this is what I like about Desmos, is it puts it right there. So we've got our 2 critical points. If we want to find the endpoints, which we're supposed to do as well, we can just click on the endpoints. They don't seem to stay, but -2, -3, and 3, -8. So we've got our endpoints. Which ones are the smallest? Well, I'd say when x is 2, y is -19. That's our absolute minimum. And when x is -1, y is 8. That's going to be our absolute maximum. So we found them. We've looked at everything. That's all done graphically. But what I want to show you is that using this, you can also, Desmos has a feature, and so does the TI-84. You can graph the actual derivative of a function. There's a similar thing you can do in the TI-84. If you can't find it, send me an email. I'll make a little video. I've done it before. But in Desmos, you just do d dx. And the reason I put f of x equals is then I just take f of x, so it refers back to it. We've actually got the derivative. And notice where the derivative is 0 at -1, that's where the maximum is. And this is something we're going to do a little bit later, is we'll look at the function and we'll try to come up with what the graph of the derivative look like. So as you do this, you're training yourself to see, here's the function, here's the derivative. Where I got a maximum, the derivative is going to be 0. The other thing we see where the derivative is a minimum, that's also an important point. That's what we call the inflection point. Okay, so we're going to talk about that later, but notice how by just looking at the graph, we can pick up a lot of diverse concepts. When we think of them individually, it's going to be a couple days before we get to that idea of an inflection point. And that's where it changes from decreasing to the rate kind of does a change. We'll talk about that later, but it's all here. All right, so we see the blue is the derivative, and then we can kind of match up. When at 2, the derivative is 0. At 2, we have a minimum, absolute minimum. At -1, the derivative is 0. At -1, we have an absolute maximum. So we see it graphically. Seeing is believing, right? And we've narrowed it down on the range. Okay, how's that? Because I'm doing a one-shot chance here. I looked through all the problems, and that's all the problems are basically find the maximum, find the minimum. So it's just doing the same thing, and I would say do the same thing. Graph them first, because then you should be able to see them, especially if you use Desmos and say, find the derivative for me, and you'll see what your answers are supposed to be, and then go back and take the derivative, because that's going to give you good practice for the mastery that's coming up. And again, you'll be able to kind of go there without the blindfold, and sort of put the blindfold on where you can't see the graph, or you could keep it up, but that you could actually take it. Okay, so now let's return here, and let's do this analytically. Okay. So we know the answers, but we're going to see that we'll get the same answers without having to graph it. And this is, like I said, my day. I was doing this stuff in the early 80s. There was no graphing calculators. There was no Desmos. We had to definitely use calculus. I think there was running water back then, but I'm not, Of course there's running water. Okay. We did have automobiles too. They were different than today, but. Okay. So what was the first thing we're supposed to do? Take the derivative so we can find critical points. Exactly. We could actually find the endpoints first if that's your preference, but that's what the list said, find the derivatives first. So we'll first find the derivative, and then we'll set it equal to 0. So derivative 3 times 2, so the 3 comes down, so that's going to give us 6x, subtract 1 from the exponent, we get 2. This 2 is going to come down, so we get 2 times 3, that gives us negative 6, x to the 1 power. And then on the 12x, we have a 1. 1 times 12 is negative 12. Subtract 1, you get x to the 0, which is 1, so that's gone. And then plus 1, derivative of that is 0, so it's gone. So there's our derivative. And now what we want to do is we want to find where is this equal to 0. One of the things is since we found that they occur at integer values, this thing should probably, what do you call it? Factor. Forget the thing. And you can see there's a factor of 6 in each of these. So the way I would do this, I would factor out the 6. Gives you x squared minus x minus 2. Divide both sides by 6, and now the 6 is gone, right? So we'll divide by 6. That's gone. 0 divided by 6 is still 0, so that's okay. And then we factor this inter part, and that's going to be negative means one's positive, one's negative. They have to multiply to give us 2. The only thing that multiplies to give us 2 is 1 and 2. The middle term is negative, so that tells us the bigger number is negative. So the negative goes on the 2, the positive goes on the 1. And remember, when you solve for these, you get x plus 1 equals 0, so you subtract 1 from both sides. So this factor is going to tell us that we've got a critical value when x equals negative 1. And this one, x minus 2 equals 0, solve that, you add 2 to both sides. So at x equals positive 2, we get another critical number, an x value that's critical. What's the second, well, this is sort of a subpoint that we're still at. Now that we've got our critical numbers, what do we do with those?
Check it out.
Check the value. Yeah, so, and we go back to the original. We don't put them into the derivative. This is, again, an area where it's easy to mess up. That's because I know I messed up everything, probably in any way it could be messed up. I've done it. So we want to go back to the original function. We want to find these function values. So we want to find f of 1 and f of 2. And again, you plug those in. I like 1. I'll do the 1. I'll leave you to do the 2 because that's harder. Right? 1 power is really easy. So that becomes, whatever power is still 1, so that becomes 2 minus 3, which is negative 1. What's that? Oh, thank you. I was going, wait, no, I was looking at the coefficients. So, right, so negative 1, okay. So it's a little bit more complicated, but not too much. So when we have an odd power, that's going to be negative. So this is, yes, negative 2. Even power, that becomes positive. So that's minus 3, minus 12. Oops, a minus and a minus make that a plus 12, sorry. And then we've got a plus 1. So it looks like we get, at negative 1, we get, that's negative 5, plus 12 is positive 7, plus 1 is positive 8. So we get the point negative 1, 8. And that's what we saw in our graph, right? And we do the same thing with f of 2. I'll let you do that, but that's, again, it's just plug it in, or put it in a calculator, or just go back to the graph and take a look at it. The important thing is that you took the derivative, set it equal to 0, and you've got these points now. And we'll just say, do the same thing, and we know that we're going to get 2, what was it, negative 19 is what we ended up with. Pretty sure, from the graph. Okay, so those are 2. And then what's the next step? Endpoints, yes, so don't forget. Now, we looked at the graph and we don't really have to worry about them because that's the nice thing about looking at a graph. We know that it's not going to occur there. But again, what we would do, okay, look at the endpoints. So find f of -2, find f of 3, check those values out, and we'll see that they're, again, it's just tedious work. Plug it in, get it, and you'll see that those are not the values, but we will see that we get a absolute max here, and that this is the absolute minimum. Okay, we'll just go through that process with each one. And again, I always, at least my preference is to start. You might want to start without the graph first, just to push yourself a little bit, but I don't like to push myself too much, you know. That's why I don't have one of those physical trainer guys, because they always yell at you to make you work hard. I don't like to work hard. So, but anyway, you do what you want to do.
Why do you check the -2 and 3 alpha values?
Because they're the endpoints, and they might be a place where there's a minimum or a maximum.
Okay.
They might be. But that's the beauty of looking at the graph. We know they're not, because we've already looked at them. Yes? Would give us. It would, because it's an endpoint. There is no. It wouldn't have a slope there. Now, even if we went a little further out, because well, let me see. So at this endpoint, we can see the derivative's not going to be 0. In fact, we really can't take a derivative at an endpoint. Even if we continued it, it certainly wouldn't be a minimum or a maximum. But it could be if that was the end of the domain, right? If it was low enough, it could be a minimum. If it was high enough, it could be the absolute maximum. Does that make sense? Okay, not sure if that. But that's the only thing we're checking them for, is they could be places where minimum or maximum, and the calculus doesn't help us because we're just kind of cutting it off there. Okay, and then the last thing, the last slide I have for us, so that I can start passing. We're pretty fast today. I could pass these back. I kind of got the same system we did last time. Let's go back here. So this is like a homework problem, and they will give you, again, they give you a function, they give you a interval to look on it. I would, again, my first thing is I would graph those with Desmos and, limit it, kind of examine it that way. They want absolute maximums. And I just want you to, this language, when they want that maximum value, they are talking about what? The Y value, the output, right? So this is a Y, oops. I told you there wasn't much, so this is a Y value. This one's easy, so they tell you it's an X value, but where it occurs or its location, that's an X value. And a minimum value, whenever you see the word value, that's a Y value. Whenever you see a location, that's an X value. Okay, so it's just, be careful about mixing those up because it could be marking wrong, and it's just that you just need to switch them. Just make sure you're getting them in the right place. Again, in the ALEC system we use in our college algebra, it doesn't, it's more ambiguous when it talks about them. It doesn't say X and Y, and it's so easy to mix them up. Okay. So we've got today, just look basically where it equals 0. Don't forget about the endpoints. There's 10 questions in WebWorks, and again, do take the time to go through and take the derivatives, because those will help you with the mastery test. And then you have till Sunday to finish up any of the previous homeworks. I will do it again, and then we kind of just want you moving forward. So, as I pass back exams, like last time, I have a list. It's just easier if you want to come down, give me the number next to your name. I got them in numerical order, and I'm faster with numbers than I am with alphabet. And if your last name starts with A to F, if you could come down first, we'll do you, and then we'll go through the groups, okay? And again, just tell me your number.
5 or 4.
4. Let's move down this way. More people can look at. So just look at the list, get your name, and then come forward.
33.
33. Oops, you're on. Oops, don't you are. You're the last of the. Thank you. I got yours. Okay. 9. 21.
14. 10.
32.
32.
Easy.
Yes, sir.
17.
17.
52.
In a moment, it's in the next step. 52.
Can't wait to go back.
Yeah.
Yeah.
Yeah. We're just A through F to
Oh,
start.
my bad.
31.
30. Well, 16. 16. Yes.
$30.
There you go.
20. Thank you. 5.
5. Excellent. There we are.
Thank you.
Okay, how about G through M? I'm not.
This is fine.
No. 210 is the only.
62.
62. Sorry. That's okay. 62.
What is it?
50?
52.
52.
36.
36 comes before 37. See, even with numbers I get messed up.
59.
59. Okay.
Thank you. 35.
35. There we go.
17.
17. 17?
17.
70.
No, 17.
17. 1 7.
Yes. Oh, is it this number?
Yes.
50.
Oh, okay. I was going. Okay. So it's gone. Yeah. So good.
61.
Thank you.
49.
49.
53.
Perfect.
56.
Awesome. You guys are almost in onward. 7. 7. 7.
64.
It's like I've known you for 2 months. Please remember your
39.
I would never even like.
63. 58. Thank you.
57. 57. Thank you.
27.
93.
Right before us.
John?
Thank you.
Me and Austin, 20.
65.
Gas.
34.
Right on time.
109.
Oh, no. You're in the next group.
Oh, that's my bad.
Let me get you. Okay.
37.
37? Right on time.
69.
68. 68.
There you go. Okay. Next group.
That's my bad. I kind of
No
forgot we
worries.
were going by groups. It's okay.
109.
109. Thank you.
93.
91?
3.
3.
Yeah.
93.
Season. Wenger.
What number?
Oh, what?
80.
80?
105 for me.
Jacob.
105.
105?
Yeah.
Okay.
107.
Okay.
87.
110. 110.
76.
Thank you.
74.
Awesome. Right on top. Oh, almost.
Thanks. 97.
113.
119?
It's 13.
13. Okay. Yeah.
Harmonics. Thank you.
Here's the last one.
83.
104.
Don't straight out that one. 100.
100. There we go.
90. 91.
73.
Right on top. And it's by the
Is it by last name?
Canvas last name.
Oh, okay.
So I know some of you, it's.
Yeah.
I think you use a.
I think I use the R. Oh, 84.
81. 81?
84.
84. Yeah.
Yep, thank you.
60. 60.
60.
Yeah. Thank you.
Thank you.
82. Thank you.
98. Good job. Good thing for stopping by, too.
No kidding. Thank you. 94. Thank you.
Ms. W?
Yeah.
Wilson?
These are ours, right?
Yes, yours to keep.
Is there something wrong?
I noticed that during the exam. understand the material? Were you just kind of checking or did you not?
I'm so nervous about this.
So we'll let it go, but just be careful, kind of guard, I got myself in this one, that's chemistry. I let the guy, because he was gonna give me a ride, so I let him look at my papers. I was as guilty as he was, so that's the thing. Okay, so I will enter the scores. I got 100, and I got a 94.
Okay.
So you both did very well, but just be sure that you're studying. Because I watch that,
Like I do all the review, but I'm just still like so nervous.
So I think she has the most favorite videos. She wrote every book.
Yeah, I can see you, but there was a few that you didn't write as much, but that doesn't mean you don't know what you're doing. I think you're more visual, but just be careful about where your eyes are.
Thank you so much.
I don't like to have to do anything with this, but yeah, so those are yours. I will record the scores when I get back, and you're all good.
Thank you so much.
This actually made my day.
Okay, good.
Can I ask you a question? So, is there any way I could get like partial credit back? Because I have all the work here, but I only circled the wrong one. So, is there any way I could get points back somehow?
Yeah. Oh shoot, where's that? Well, let me disconnect. Oops. Oh,